Hi, I'm George, and I'm a program manager in the Silicon Platform team of the CoreOS team at Microsoft. Arvind and I are going to present USB accessories and related work our buses team added to Windows 10. This talk is really about enabling you to build apps that can connect with hardware from the past, like a 30-year-old natural gas meter that might connect to an old RS-232 connector like this, or prototype new hardware like a temperature sensor that's connected to an Arduino like this. How cool would it be if you could write one app that works on a phone that supports USB accessories, a desktop or a laptop, as well as an embedded system like a Miniboard Max or Raspberry Pi V2? At the heart of all of this is Windows 10 including support for USB accessories, as well as the Serial Device Communication Protocol in our new Universal Windows App Platform. That's what we're going to cover in this talk. Windows 10 adds USB accessory support. Yep, now you can connect plain old accessories like this USB flash drive to a phone running Windows Mobile. And it also adds a new Universal Windows App namespace for serial device communication, prevalent in old hardware like RS-232, as well as future devices not even prototyped yet. Both items, the USB accessories and the serial investments, are a direct result of us acting on customer feedback from the maker community, as well as many app developers and accessory developers. Together, these two enable you to build apps that connect with both hardware from the past and the present, and perhaps even the future. I'll challenge the audience to create a device that bridges the two. Once hardware catches up, you should be able to physically connect a Windows 10 phone using USB Type-C to a 30-year-old natural gas meter. Not exactly a time machine, but kind of. So our agenda basically revolves around these two topics. I'm going to cover USB accessories for both typical and vendor-specific accessories and app development for them, and Arvind's going to go over the serial communications namespace. Let's start with USB accessories. Windows 10 Mobile SKU adds support for USB-connected peripherals on new phones and tablets by USB dual role support. Dual role basically means the device can act as a peripheral or a host and dynamically switch between the two of them. Our team's been working with Silicon partners on this support, so a new wave of Windows 10 devices will support USB accessories when Windows 10 launches. As developers, you can build physically connected accessories using open industry standards without per unit royalties or special discovery protocol, unlike other platforms, leveraging the power of our Windows Universal App Platform. To understand USB accessories, let's first look at the types of accessories that we targeted. There's basically two types of accessories we focused on enabling. First, there's typical accessories people just use every day, like a flash drive. Second, there's a set of developers who develop unique functionality. Think of a smart cover for a phone. I'll call these vendor-specific accessories because they typically require an app from the accessory provider. Let's first start with typical accessories. So this slide basically covers the types of typical accessories that the mobile SKU supports natively. Typical accessories have APIs and built-in device drivers in the OS that standardizes commands and responses across vendors. For example, flash drives or microphones from different manufacturers, or a credit card reader from manufacturer A and manufacturer B. The key is that you can develop one app that works regardless of those things. Secondarily, many of these accessory types support, like browsing files or recording audio, also include built-in user experiences in the Windows mobile platform. So this slide contains a list of the accessories that are natively supported on the mobile OS SKU, which explicitly support app development. And you can see the namespaces that you can use to access them. It's also worth understanding there's a set of natively supported accessories, like for productivity scenarios, like keyboards and mice and network adapters, that aren't directly of use to app developers. Well, seeing is believing. Let's take a look at the demo. So I'd like to demonstrate just using a USB flash drive like this one here on a handset running Windows 10 Mobile. I'm getting ready to go on a business trip to Europe, and I want to catch up on some videos from the WinHEC developer conference that I missed. So I can copy the MP4s onto this USB flash drive so I can watch them while I'm in flight. This is a development handset that supports USB accessories via dual role support. Before I leave, I copy the files onto this flash drive so that while in the air, I can watch them. And let's see, you can bring up the File Explorer. You can see some of the files there on the attached card. So let's catch up on some of Don Box's keynote from WinHEC.
Please welcome Don Box, Microsoft Distinguished Engineer.
So now I can binge watch all of these videos while I'm on my plane. And even better yet, I can have more videos than the phone natively supports in storage. Next, let's look at vendor-specific accessories. Those are the ones that typically require an app from the folks who developed the accessory. Examples include smart covers, fitness devices, robots, smart toys, and the like. The app commands are commonly unique and not standardized across different hardware manufacturers, and the drivers do not often fit into a well-defined class. Let's look at an example. So I'd like to demo an Arduino on a USB handset. This is a very simple future USB accessory on a development handset that supports USB dual role. It's built with the popular Arduino prototyping platform that many folks use to make new accessories and things. Here's a super simple app that reads data from a temperature sensor and writes data to the LEDs on the board. You can see that I'm controlling the different LEDs by just flicking these toggles here. All the hardware that I'm showing costs roughly $40 and can be ordered from Amazon. And the app that I'm showing, as well as the sample source code for the microcode for the Arduino and the wiring diagram, we plan to publish in early June. Now, this is just a simple example of something you can easily prototype using an Arduino and this support in Windows 10. You can also do way more advanced things. For example, some of our quality folks are actually working on a way to build a voltage meter using something like this to actually measure the quality of the USB dual role functionality on new handsets. So what does Windows offer for developing apps for vendor-specific accessories? So Windows 10 includes HID, serial, and USB APIs and drivers built into the Windows 10 Mobile SKU. These APIs are part of the Universal Windows App Platform, so you can use them on PCs or embedded systems or even phones, leveraging your prior familiarity for developing for them on these new form factors like phones and embedded systems in the language of your choice. So these namespaces and these SDK samples, we're providing at build, and they also work on handsets that support USB dual role, like this development handset. Here's an important point for you to understand about developing accessories for vendor-specific accessories. It's super important to make sure that your accessory installs the right driver so that our APIs can access it. Your accessory can use these methods. There's a set of compatible IDs, and we'll provide more in the resources later about how your device can report itself so that these drivers will just install. It's important to recognize that our mobile SKU does not support installation of vendor drivers like from Windows Update. It's basically more like a phone instead of a PC. The USB serial driver that we include in Windows 10 in particular addresses key customer feedback on improving reliability and installing against these compatible IDs on boards like Arduinos that lots of people have given us some very good feedback on. All three of these drivers cover future accessories and hardware pretty well. All three drivers cover future accessories and hardware pretty well. There's one important scenario for past hardware I'd like to challenge the audience to address. Customers need to access hardware like 30-year-old natural gas meters with RS-232 connectors like this. And they typically use a USB to RS-232 adapter cable to do so. I'd like to challenge the audience to build one of these cables that actually reports the compatible IDs that our built-in USB Serial.sys supports natively. The first company to do so will get recognition on our API documentation as well as the web page this video is hosted on. So how can you start developing apps for USB accessories today? It's pretty simple. You probably already have most of the stuff that you need. Start with just developing a universal app on a desktop or a laptop that has a USB port. Next, just make sure that the UX lays out properly on different form factors like a handset. And then finally, once they're available, get a dual role capable mobile device to test your app with accessories. So how can you do that last part? Find a dual role capable device. It's actually a very good question. Now, especially before these devices hit the market, you need a new phone or tablet that your manufacturer says supports USB dual role. If you're buying a new one, look for a device that your manufacturer says supports USB dual role. If you already have a device, the Windows 10 user experience will indicate it. Like this screenshot here from our USB settings page tells us that the device supports USB connections to devices like keyboards and mice. Well, that's the USB accessories part of our talk. Next, I'd like to introduce Arvind, who's going to present the Windows.Devices.Serial Communication namespace. Arvind?
Thanks, George. Hi, my name's Arvind. I'm a software engineer. I work with George in the buses team in the operating systems group, and I'm going to talk about serial communication using WinRT. So George gave you a good introduction about how now we've enabled USB accessories to work with a plethora of Windows devices like phones, tablets, and embedded devices. I'm going to focus on a specific aspect of it, namely how do you talk to USB serial devices or serial devices in general using our new WinRT namespace that we've introduced in Windows 10. So let's start with an overview. In Windows 8.1, if you recall, we introduced the notion of protocol level access. What protocol level access implies is you can use standard protocols like HID, USB, Bluetooth, Bluetooth Smart to talk to a device using Windows runtime. This enables a growing community of hardware developers to write apps for their either custom devices or well-known devices using technologies that are simple and easy to use. To add to that long list of protocol APIs, in Windows 10, we add serial communication to the list. And it's a little bit ironic because serial communication predates some of these protocols, but hey, better late than never. And this portion of the talk focuses on the nuances and the intricacies of the Windows Serial Communication API that is supported in Windows 10. So let's go back a little bit and understand why did we decide to add serial to the protocol level APIs. Now, we recognize that there is a really strong interest in the developer community as well as in the retail world to communicate with serial devices. Serial devices aren't going away. There are a lot of them. You can see from the little Arduino to commercial enterprise level gas meters and things like that, that serial communications are part of our world. And it's really more important nowadays when we talk about embedded systems where they have serial controllers, UARTs and stuff like that on them, that serial communication is still part of the technology space. Moreover, there is an existing ecosystem of Win32 apps that you can use to talk to serial devices. Everybody knows that you can write a Win32 app that can open a COM port and start sending data and reading data from your serial devices. And especially with the advent of the Internet of Things and embedded systems, more and more of these devices are there in the marketplace. So with the promise of Windows 10 and the Universal Windows app, it makes perfect sense to bring Serial into the WinRT fold. So this slide summarizes the new experiences with serial communication that are there in Windows 10. As with all other protocol APIs, there is a built-in device discovery model, which allows you to discover, access, and instantiate your serial devices. There's, of course, the new Windows Runtime API, which simplifies communication with your device. And the final point, which is that it works with Windows Universal Apps, which means you can write it once and deploy it everywhere. So you can see that you don't have to do anything specific for making your app work on phone or a tablet or on a desktop or on an embedded device. So before we go into the depth of the talk, it would be good to sort of set some prerequisites about what would be useful for you to absorb the content of this talk. First of all, it's important to know a little bit about how serial communication works. And a lot of the audience who's interested in writing WinRT apps for serial are probably familiar with the Win32 programming interface. It's probably good to know about that. There's also the .NET serial programming interface. So familiarity with those would help in absorbing the content of how WinRT works with serial as well. And of course, since we're in the realm of the Windows runtime, brushing up or being familiar with some concepts which are unique to the Windows runtime, like async operations, device operations, is also useful. So let's look at the architecture of how this is all laid out in Windows. So you have your Windows Universal Windows app right at the top of this layer cake. This uses the windows.devices.serial communication API, which is the runtime component. And these together run in the app container process, which is where all Windows Universal apps run. The runtime component uses the native serial layer, and by that I mean just a bunch of ioctls. There's an existing ioctl interface for serial, and we just reuse that. And there is also a device broker component. The ioctls communicate with the device below, and the device broker sits on the side. And we'll go into a little bit of detail into what exactly the device access broker does. So the device access broker is actually an OS component whose role it is to do some basic bookkeeping and gatekeeping for device access APIs. To draw parallels with the Win32 or the .NET world, where there was no real gatekeeping, like if you were able to discover a serial device, you were able to open a handle to it and start sending it I/O. However, with Windows apps, we uphold certain app container principles and promises and user promises, and hence the device access broker acts as the mediator or the gatekeeper before we allow access using these opaque pipes. So with that is set, let's go and look at a demo about how exactly all these things are laid out. All right, what we're going to demo here is a simple Windows Universal app that has been developed in Visual Studio that uses the Windows serial communication APIs. And this app will work with a Arduino development board, an Arduino Uno to be precise, which is right here. The setup is really simple. We've wired 4 LEDs and a temperature sensor to this Arduino Uno board, and it's connected via USB to the mobile handset. So let's see what exactly it does. So I'm going to launch the app, and it's just a simple app which has controls for a bunch of LEDs as well as getting the temperature. So the first thing I'm going to do is actually connect to the device, and you can see that it shows here the device has been connected. And then I'm going to start by toggling each of these LEDs. So when I toggle an LED, you'll notice that the corresponding LED on the board has just lit up. All right, so let's start by toggling some LEDs on the board. So I'm going to press these LED buttons, and you can see that they alternatively go on and off. And I'm going to turn them on again, one by one, and so on and so forth. So, and there's a little temperature button here, which because there's a temperature sensor that's wired up to the Arduino board, I'm just going to press this, and it's going to show you the current temperature. So you can see that it's reading 22.31, and then it keeps varying. So I'm just going to maybe just press this slightly and see if I can get it to heat up a little bit, and then see if I can press the temperature and see. So you can see it varied slightly. So it's fairly straightforward. It's just reading and writing to the Arduino board. Now, interesting. Let's see if we can now the same app. Let's see if it's make it work on a laptop that I have connected here. So I'm going to unplug this USB cable, and I'm going to plug it into my laptop. So the same app I'm going to now launch from my laptop, and you'll see that it works exactly the same way as we saw on the mobile handset. So I'm going to connect to the device, and I'm going to toggle the LEDs back on. There you see. It's on and off, so on. And the temperature sensor works as well. All right, so that was a mobile handset, a desktop. Now let's add an embedded system into the mix. So I'm going to move the Arduino, and I'm going to connect it to a MinoBoard Max, which we have here, which is also running a version of Windows. And you'll see the same thing happening. And now we're going to launch the same app from a MinoBoard Max, which is running a version of Windows. And you'll see, and we've hooked up the Arduino to the MinoBoard now. And I'm going to now launch the app. I'm going to connect. And then I'm going to start by toggling the LEDs back on and off again. And there you go. So you can see the power of Windows Universal Apps now, how you can write your app once, deploy it on a variety of systems, form factors running Windows, and get the same experience using the new Windows runtime APIs. All right, now that you saw the cool demo, let's delve a little bit into the nitty-gritties of what it took to get this all working. The way we structure the remainder of this talk is to provide a walkthrough of what it actually takes to build a device app for a serial device. So the advantage of this step-by-step process will become really apparent because there are a few key pieces that you need to get right in order to successfully communicate with your device. So there are 4 main steps that most apps will tend to get to follow to get started. And this is pretty much universal across most device apps that you will encounter in the Windows runtime. First of all, you need to declare what is called a capability. So the capability declaration is a means to express the intent of what the app will use. It could be some really high-level construct like internet or location. But since we're actually focusing on device-specific stuff, what we're going to talk about, what we're going to use is device capabilities. The next step is to find the device that you're interested in and actually instantiate it, which is where device discovery comes in. Once you figure out the device that the particular device or devices that you're interested in talking to, then you can instantiate the device, and of course, you can start communicating with the device. And finally, when we are done, we, of course, clean up. So let's look at each of these steps in a bit more detail. The first one is, like we mentioned, the capability declaration. The capability declaration resides in the Apex manifest. There is a package.apex manifest file that's generated with every Windows Universal App solution. and inside that you have to declare a device capability. For serial communication, the top level device capability is just the full name, which is serial communication. Within that, there are two sub capabilities. Firstly, it's the device ID, and the second one is the function type. So for serial devices, there are two types of device IDs you can use. One is a device ID of any, which implies you are interested in finding any and all serial devices. Or alternately, you could specify a device ID with a USB vid and a PID for a USB serial device like the Arduino we just demoed. And this is pretty much the USB vid and PID. And then in the function type capability declaration, you need to declare the particular function on the device that you're interested in. For example, if you had a multi-function device, you would be interested in talking to the serial part of it, hence the name serial port is what you would declare in the function type declaration. All right, so we have the device properties. Let's see how they look like in the Apex manifest. And this is simply an example of a package.apex manifest file in Visual Studio. And towards the bottom, you can see a device capability declaration, which shows the serial communication top level namespace as well as the individual device ID declarations. And here are two examples of the same Apex manifest. The first one shows you how to declare a device ID of any and a function type of serial port, and the second one uses the USB vid and the PID, followed by the function type of the device, which is still serial port. So that's straightforward enough. So once you have the capability declaration, Windows and the app platform knows that you intend to talk to serial devices, maybe a particular one or all of them. So then we move on to device discovery. So for serial devices, the way Windows has traditionally treated them is by the abstraction known as a COM port. A COM port is essentially an identifier for a serial device when it's plugged into the system, and it's assigned in sequential order by a component within the OS known as the class installer or the ports class installer, which gets handled just during when the device is installed, when you plug it in. And the COM port also gets assigned a symbolic link, which apps can use to open a handle to it. Now, there are some problems with this approach. Obviously, a COM port really isn't telling us a whole lot about the device. It's just abstract out any detailed description or particular types of devices. All you really know is about, hey, I have some serial device which is plugged into COM1, COM2, and COM3. And of course, when you want to do real discovery, since the COM port number can vary across systems where it's plugged in, you really can't rely on the device getting assigned the same COM port number across systems, which means you can't really identify the device in the same way across the board. So to alleviate all these problems and to fit in with the Windows runtime model, there is a much more augmented device discovery pattern that we use. Now, the definition of in Windows runtime of a serial device is now expanded to more than a COM port. It can be some kind of device identifier. For example, if you have a USB serial device, you can specify it using, if you know its vendor ID and product ID, you can discover it using that. Or if the serial device had a bridge that it was using to connect to the PC, maybe it's the vendor ID, the product ID of the bridge. If, for example, you had a way to display the friendly name of the device, or it had some more descriptive name like 3D printer or Arduino or so on, then you can discover the device using that friendly name, assuming it is set appropriately. So with this augmented discovery model, you will discover that finding devices is now a piece of cake, and it can be deterministic. So how do you go about actually discovering the device? The first thing we need is a selector. A selector is just a formatted string using a syntax which we call AQS, or Advanced Query Syntax. This is a pretty standard mechanism that we use for all device enumeration APIs within Windows. Fortunately, we have a couple of static device selectors that we've built into the serial communication namespace. And there are 3 device selectors, which are just outlined here. The first one, without any parameters, finds all serial devices on the system. Or you can decide to use a device selector with a string, which is a port name or a friendly name, or a device selector with the USB vid and PID. And then once you have this device selector returns back in AQS, you can pass that AQS to a device enumeration APIs that are built into Windows in the devices.enumeration namespace, which is the find all async or the create watcher methods, and it'll give you back a list of all devices that it found. Specifically, it gives you back a list of device information objects. And then finally, you can walk through the list of device enumeration objects or find the one you're interested in and actually open the device, which in WinRT is by calling from ID async. And from ID async under the covers essentially just opens a handle to the device and gives you back an object that you can start using in your app. And of course, you can use that to send I/O to the device. So let's look at how it looks in code. Like we just went through, you have a selector. In this case, we are using a selector which uses the USB vid and PID. There's another example of a selector which uses the friendly name, which can also be COM1 if that's what it shows up as. And then we call find all async to find all the devices on the system. And then to instantiate the device, we call from ID async, which gives you back an actual serial device object that you can use. A quick word here. You need to worry about the case when the device is null, and we'll go into a little bit of detail a little later in the slide. All right, so when you call from ID async, what really happens? We have a bunch of checks that we do before we grant access to the device. So when you call from ID async, it means Windows is going through those checks and giving you a handle that you can now send I/O over. But before that handle is given back, we have to do a bunch of runtime checks. Of course, we check that you have declared the right capability declaration in your Apex manifest, which, if you recall, was the intent to talk to a particular device. Then we also check whether there's any OS policy restrictions in place to let you talk to a particular serial device. We also look for exclusivity. Serial devices are exclusive in nature, so if one app has it open, then another app will get access denied. So we check for exclusivity. And finally, there is this notion of consent or dynamic access. So quick word on consent, because this has evolved from Windows 8.1 to Windows 10. We've streamlined the requirement for consent in Windows 10. Specifically, there is no longer a runtime pop-up that shows up that is presented to the user before to actually grant access to the device. Instead, for serial and HID and USB and on most device protocol APIs, consent is granted automatically, and the user can actually change that by going to the PC settings page under privacy and dynamically revoke or grant access to the app before giving access to the device. Now, as a result of any of these steps, if it's somehow discovered that the device handle cannot be open for any of these reasons, what you will get back is a null serial device objects. So what do you do then? So if you encounter a situation whereby from ID async gave back a null object, then you can optionally call these other device access information APIs to figure out a more detailed status as to why you were not allowed to open a handle to the device. Again, this is an optional step. It's not a must-do, but if you were to, if you wanted more information on what exactly happened, here's the way to do it. All right, so now we've gone from capability declaration, we've talked about discovery and instantiation. Let's talk about communication. So communication has 3 steps, essentially. You have basic configuration. You want to configure the serial device, which, if you're familiar with serial devices, is things like baud rate, parity, stop bits, handshakes, etc. And then reading and writing from the device. and we overload existing concepts in the Windows runtime which are input streams, output streams, data readers, and data writers. So let's look into communication. So the first step, like we talked about, was configuration. In this case, here we have a bunch of configuration parameters like baud rate, stop bits, and parity that you'd know ahead of time that the device uses. And then writing and reading. So the first part is writing. So if you wanted to write to the device, you would use the output stream property that's there in the serial device object and fill in the data writer that you create from this output stream with whatever. In this case, I'm just showing you a way to write hello over a serial port, and then you can call load async on it and send the data on that stream. And you can check back to see how many bytes were written. Similarly, reading from the device is using input streams. So you would create a new data reader. You would specify how many bytes you want to read from the data reader, and then you would call load async on it. And in this case, I'm just reading the same string back. So if this was like hooked up in a loop back configuration, you would just see hello being transferred across the wire. So that's really what there is to reading and writing. So it's fairly straightforward. There are a few other events and so on, which we've left as an exercise for the reader. Finally, we should always remember to clean up after we're done doing any kind of I/O with the device. So the first thing the app must do is to close the serial device, which underneath the covers essentially ends up closing the handle to the device so that other apps or other entities in the system can start using that device again. And an important nuance that we should remember for close is to be aware of language-specific usages about how to close a device. And we look at that again here. So closing the device in C++ looks like just a delete, whereas in C# you actually have to call dispose on the serial device object. Another point that is important to also keep in mind is app suspension and resume. Windows apps, Windows Universal apps, are subject to suspension and resumption. So if they were not in use, they can be moved to the background and brought back into the foreground as the user switches back and forth. So what should you do in your app when it's suspended? If it is suspended, first of all, you must register for the suspension notification. And in the notification, you must close the serial device because it will get invalidated and the handle will no longer be valid. It should not send any new I/O. And when the app gets resumed, it must reopen the device all over again and start from scratch. Well, not really start from scratch, but at least you can cache the device information object you got and reopen the handle to it. So with that all said, let's go back and look at what it took to write the app that we demoed on the Arduino. And we'll walk you through each of these steps that we talked about in the slides and see how they look in code. All right, so let's look at each of the steps that we talked about in slide in code and see how this all plays out. So like we mentioned, the first step, this is the same app code that we were using to talk to the Arduino in our demo earlier. So all of this will be available in early June, and you can download this code, the app code, as well as a sketch for the Arduino and see how this all works together. So here's the first step, which is connecting to the device, finding and connecting to the device. Like we mentioned, we use a selector, and the selector this time is we specify the Arduino vid and the PID. The selector returns a formatted string in the AQS format. We pass that to findAllAsync, and that gives you a collection of device information collection objects. Since in this case this is a pretty simple app, there's just one Arduino connected. If we do have a single, if the count is greater than 0, we just open the first one in the collection. And once you open from ID async, if that succeeds, that means you were successfully able to open a handle to the device and you got a non-null serial device object. Then you can go ahead and configure the serial device. In this case, we set a bunch of properties on it, which is the baud rate, parity, stop bits, etc. And the device is ready to be communicated with. So now you can send some I/O to it. So let's look at reads and writes. So we look at writes first. In this case, let's look at particularly how the LEDs were toggled on and off. So we have a function here, which is the write LED on command function. So it's a pretty straightforward protocol. We create a new data writer using the output stream on the serial device object. And we write a string which is LED on followed by the LED number. Since there are 4, this would look like LED on 3. And then the sketch would, or the firmware on it would automatically set that particular pin to high. That's really what happens at the device level. So I have a data writer. I fill it in with a string, and then I call store async on it. And then this goes ahead across the stream, and then using the APIs, it will send the same command down to the device. And we have an LED off parallel to this, which is exactly the same, except we just call it LED off along with the LED number. So that was writing, and reading follows a similar pattern. Reading was when we looked at the temperature and how we got the temperature. We have an output stream here, and the first thing we have to do, actually in this particular sketch, we have to actually send the string temp down to the device before you can actually read from it. So this is what it actually shows. We actually send the string called temp, and then we read back from the device. And reading, like we just talked about earlier, is setting up an input stream with and a data reader, instantiating it, reading 7 bytes from it, that's what the protocol returns, and then displaying what was the number of bytes read as text, which is what the temperature is about. And that's really all there is to it. We talked about finding the device, discovering it, opening a handle to it, configuring it, writing to it, and reading from it, which is really all serial communication is all about. All right, so we looked at the demo. We looked at how it looks in code. Let's talk about a little bit about additional features that are there as part of this API. In particular, we want to talk a little bit about background tasks, because that's also a construct that's built into the Windows runtime. Apps can do long-running operation using background tasks. You can use a bunch of triggers that are well-defined triggers that are there part of the system, like the system event trigger, the control channel trigger, or the device use trigger. You can use any of these triggers to trigger a background task that you can run and talk to your serial device. An important note here is that tasks are not throttled like other system background tasks. There is no CPU time quota, but the caveat is there that it may run with reduced priority to keep the foreground apps responsive. An important note here is that this actually applies across all device protocol APIs like HID, USB, and serial, of course. So you can now start using use background tasks without actually getting throttled. Debugging, of course, there's debugging built into the API. So if you encounter any issues, you can actually do WPP tracing for the communication API DLLs as well as the device broker. There are details on our MSDN page regarding this. And here are a few related sessions that are relevant as far as this talk is concerned, which you might want to take a look at or look at their recordings for.
So I'd like to recap and leave you with a few resources. First, for developing apps for typical accessories on our mobile SKU. Just remember, these are accessories that just work with the OS, and we have the following namespaces for them. It's for audio devices, removable storage and files, point of service. So check out the MSDN page and the namespace documentation, as well as the samples for these. Next, for vendor-specific accessories, these are the namespaces, HID, the new serial communications namespace that Arvind just walked you through, as well as windows.devices.usb. And all the SDK samples for these are also universal Windows app platform samples that work on all the different platforms and form factors that we just showed you. And finally, just want to leave you with a simple call to action. So if you're developing USB accessories, just start out developing a universal Windows app on a desktop with a USB port. Make sure that the UX lays out properly on a mobile phone, and then once available, get a dual role capable handset to start testing your accessory with your app. Also, be sure to make sure that your accessory declares the right hardware ID so it can work with our in the OS box drivers on the mobile SKU. Because remember, our mobile SKU is more like a phone than a PC. And lastly, your feedback is super important to us. Truthfully, we wouldn't have done any of this work without your feedback. It's kind of where it all starts. So if we happen to be missing anything, please feel free to email feedback to busapifb@microsoft.com so we can stay on top of what else matters to you folks so that maybe next year at Build we can talk about that. Thank you so much.
Thanks.